Hello everyone, I'm Kamile Petrauskiene, a PhD student, and my co-author is Professor Jolanta Dvarionine. We are from Kaunas University of Technology, Institute of Environmental Engineering. Today I will present my research topic, Comparative Environmental Life Cycle and Cost Assessment of Electric, Hybrid and Conventional Vehicles in Lithuania. First of all, a little bit of introduction. European Commission has set the targets for the European Union to reduce greenhouse gas emissions, promote renewable energy sources, and increase energy efficiency. Lithuania has a national energy dependence strategy where the desired results in Lithuanian energy sector are stated. For example, one of them is to increase the share of electricity consumed from renewable energy sources compared to final electricity consumption to 30% by 2020, 45% by 2030, and 100% by 2050. Electrification of city transport and the use of renewable energy sources in transport system have become leading trends for sustainable transportation. And passenger cars are one of the main contributors to climate change, air pollution and noise in the cities. And my interests are measuring the impacts on the environment through life cycle perspective. Therefore, for my analysis, I selected different engine passenger cars. And here are the aims of the study. To evaluate and compare the environmental impacts and economic cost of battery electric vehicle, hybrid electric vehicle, and internal combustion engine vehicles powered with diesel and petrol, to analyze the electric cars operation stage under different electricity generation scenarios that are forecasted for the years 2015-2050 in Lithuanian context, to assess the most environmentally and economically preferable electricity mix scenario and generation technologies under which the environmental load and economic cost would be the least. Then methodology. Life cycle assessment and environmental life cycle costing methodologies used. They are both aligned with the ISO standards on LCA in terms of system boundaries, functional unit, methodological steps, and considers all stages in the life cycle. In accordance with the standards, the analyses were performed in the following main steps. Definition of the goal and scope of the study, identification of functional unit and system boundaries, life cycle inventory analysis, and life cycle impact assessment and interpretation. Scope of the study. The scope of the analysis represents a complete life cycle assessment, which includes the fuel cycle as well-to-wheel analysis and the vehicle cycle that follows a cradle-to-grave approach. A fuel cycle combines stages from energy resource extraction until energy conversion, and equipment life cycle combines stages from material production until equipment end of life. Now I will present life cycle impact assessment method. The recipe method at the midpoint and endpoint levels was used to perform the impact assessment. For this analysis, database EcoInvent 3.5 and CIMAPRO 9.1 software was used. Recipe method at the midpoint level shows the results at 18 impact categories, while endpoint level combines these impacts categories into 3 damage assessment areas as damage to human health, ecosystems, and resources. Inventory analysis. This research aims to reveal the real situation in Lithuania, so the passenger cars models has to match one of the most popular models that are registered in the market. According to the statistical data of Lithuania, the most popular electric car is Nissan Leaf, hybrid electric car Toyota Prius, and diesel and petrol cars are Volkswagen Golf. These passenger car models belong to the medium-sized class, are similar in weight and length. Therefore, they are suitable for a comparative life cycle analysis. Functional unit of 1 kilometer driving distance is determined and the impact is assessed for 150,000 kilometers driven distance. Environmental impacts are calculated for such a life cycle, ensuring that electric car no battery replacement is required. For the battery electric car, it is very important to know how electricity for charging the battery is produced. For this reason, the impact of battery electric car is calculated under different electricity mixes and electricity production technologies. This table shows the proportions of electricity production in the energy system by source in Lithuania for 2015-2050 that were prognosticated by Lithuanian Energy Institute. 2000 mix consisted of 42% natural gas as a main source, then 5% of oil, which will be eliminated in further scenarios. And for example, in 2030, electricity mix is composed mainly of wind and biomass, while in 2050, the main electricity generation sources will be wind and solar. Here are results of life cycle assessment of battery electric vehicle, hybrid electric vehicle, and internal combustion vehicles at the midpoint level. In this slide, the diagrams show comparative life cycle assessment results when battery electric vehicles electricity mix is 2015. The environmental impact categories were determined according to the categories where the burden was the greatest in the analysis. So these are the 6 ones. The first graph shows global warming, second one ionizing radiation, then human cancerogenic toxicity, human non-cancerogenic toxicity, then fossil resource scarcity, and land use. Life cycle assessment at the midpoint level showed that throughout the whole life cycle, production, use, and end-of-life stages, battery electric vehicle of 2015 electricity mix is advanced in ionizing radiation and fossil resource scarcity, while hybrid electric car and both internal combustion cars had lower impact in global warming, land use, and cancerogenic and non-cancerogenic toxicity. This graph shows the results of well-to-wheel analysis of the same passenger cars at the midpoint level. Impact on the environment for the battery electric car depends on electricity production mix. Therefore, here I present with well-to-wheel analysis showing the impact from energy resource extraction until operation under different electricity production scenarios. For example, in the year of 2015, due to the use of oil and the biggest share of natural gas, this electricity mix was the most polluting. Year of 2030 is expected to be one of the most environmentally friendly, as 4 of 6 impact categories from here are the least due to the use of biomass and wind energy as main sources. Moreover, solar and wind energy will be actively used as the main sources in the scenario of 2050. Therefore, this scenario is one of the desirable as well as in all impact categories are among the lowest. Results of global warming show that battery electric car with electricity mix of 2050 is about 60% less than a petrol car and 25% less than diesel car. The environmental life cycle assessment was also performed according to the recipe method at the endpoint level. The results summarize the total environmental load as damage for resources, ecosystems, and human health. The results reveal that a petrol car has the highest environmental damage. Hybrid and electric car with electricity mix of 2015 has almost the same environmental damage, which is 14% less than petrol car. Next comes diesel car with 10% less impact than hybrid and battery electric cars, Furthermore, battery electric car with electricity mix scenarios from 2020 to 2050, which are composed mainly of renewable energy sources, have the least environmental damage. Now I'd like to present the results of life cycle costing in order to assess the economic side throughout the whole life cycle manufacturing, use, and end-of-life stages. The graph shows the results of a comparative life cycle cost analysis of the same passenger cars from consumer side under Lithuanian conditions. Manufacturing phase includes acquisition and registration tax. Operation phase includes maintenance and fuel price. End-of-life phase includes only the registration tax. A service of old cars, discard for treatment and recovery is free of charge, therefore it is eliminated. The results show that hybrid and battery electric cars have the highest cost because of the high purchase prices, while internal combustion vehicles have the lowest ones. But comparing the operation stage, it is obviously that electric car has about 37% less cost than diesel car and 60% less than petrol car. It is assumed that electric car is charged at home at an average cost of electricity. But operation for the electric car owners can be even less because most of public charging stations are free of charge. This year, a financial incentive has been implemented in order to promote the purchase of electric passenger car. There is a possibility to receive a compensation of 2,000 euro to purchase a used electric car and 4,000 euros for the purchase of a new electric car. Therefore, I want to present the same results in the table, but with a compensation included. In comparing the total cost, here we see that results that electric and diesel cars are the most competitive ones. There, the total consumer life cycle costs are about from 5 to 13% less than others. Then I will present the, another diagram which will show some the results from not only consumer side but manufacturer side. It's very important to look through life cycle costing not only from consumers but also from manufacturer side. So this analysis combines manufacturing phase, which includes passenger car and batteries production, operation phase, which the fuel production and distribution, road and car maintenance, and end-of-life phase with treatment of glider, powertrain, internal combustion engine, and batteries. The values we obtained using OpenLSA software, another one software, the EcoInvent database. But the data or the database are provided for the year of 2005. Accordingly, due to the data limitations, the results may differ from the present times. Nevertheless, I wanted to highlight that these results are similar to the graph before in the way that electric car has the highest cost in production stage and the least cost in operation stage. And the last thing I wanted to present is the graph showing electricity production cost for 2020-2050 scenarios that are prognosticated under Lithuanian conditions. These costs also include investments for the technologies. The graph reveals the cost of 1 kilowatt-hour electricity generation under different time intervals of a day. This is important for the battery electric car owners for charging the battery at the most cost-effective price. Here we see that during all the scenarios, the most rewarding time is from midnight till 7 a.m. In conclusion part, I have highlighted the main results of my research that I already told, and I let you to look through my conclusions individually. And this is the last thing what I wanted to show you, and I hope you enjoyed my presentation. Thank you all for your attention, and I wish you enjoy the rest of the conference.